So for any given molecule, you get a series of molecular potential energy functions, which depend on the nuclear coordinates. So if we're dealing with diatomic molecules, that just depends on the distance between the two nuclei, the internuclear distance. So here you have potential energy as a function of R, and here's your R. And this one is in angstroms. This particular diagram is for the SR2, diatomic strontium molecule. Okay, so the lowest possible value. Okay, so the potential energy curve down here, the lowest possible potential energy curve is what you would call your ground electronic state. So this is your ground electronic state. Okay, so each of these functions, so this would be an excited electronic state. Okay, and this is another excited electronic state. Each point on the curve, any point on these curves would actually represent a wave function, okay? Since your wave function depends on R, okay? And it corresponds to one wave function and one electronic energy. And the lowest possible energy value within a given electronic state is called the TE. So generally you would, since potential energy is relative, generally you would set the TE for your lowest state to be 0. Or if you want, you can use the limit, the asymptotic limit of your ground state to be 0. So there's two ways you can go about doing that. You just have to be, you just need to specify which one you're referring to. Okay, but your lowest energy value for a given electronic state is your TE. So this value right here is the TE for this particular excited electronic state. Now, what about the total energy of the molecule? Well, the total energy of the molecule is just the electronic energy, okay, plus the energy due to the motion of the nuclei. All right. So how do we calculate the energy due to motion of the nuclei? What we do is we replace the electronic energy operator in our Hamiltonian, okay, the kinetic energy operator for and the potential energy operator for your electronic energy by and your V potential energy of interaction between the nuclei by this potential energy term. In other words, we imagine the nuclei now as moving through a field of a charge cloud, basically, where you can imagine your electrons are all smeared out. Okay, some places there's a higher concentration of electrons, in some places lower concentration, depending on what the electronic state is. So imagine now your nuclei is moving through that field, force field. Okay, so the net effect is that potential energy curve, that potential energy that the nuclei will be experiencing different potential energies as they move through that field. Okay, so the total energy then just becomes whatever the electronic energy is, plus the motion of the nuclei, which is affected by the electrons, right, can be described as, since we're dealing with just the internal motion, the relative motion, vibration and rotational energy. So vibrational energy and the rotational energy. Okay, so the vibrational and rotational energy would be something you would calculate once you figured out the molecular potential energy. All right, so just illustrate that with the case of hydrogen. All right, now in this illustration right here, this red curve is the potential energy of interaction between the two nuclei. So you have 1 over 4 pi epsilon naught plus E times plus E, charge of the nucleus times charge of the other nucleus divided by the distance between them. This is the distance, this is in picometers. Okay? That is the potential energy of interaction between two protons. Right? Now, if you were to do the calculation for the ground electronic state of hydrogen, so at this particular distance, let's say at this distance right here, the lowest possible electronic energy you calculate would be something like this. At this distance, you'd calculate that value. At this distance, you'd calculate that value. Okay? So if you have the electronic energy plus this potential energy of repulsion, you'll be getting this molecular potential energy curve. So this thing right here is a potential energy curve for the ground electronic state of H2. Okay, so this blue curve on this diagram. That's what you'll see. That's what you'll get. And one characteristic that you'll find, one common characteristic of these potential energy curves for molecules that, for atoms that tend to form a bond, is that they have this characteristic shape. Okay, so that's, we can refer to that as a well shape. So we say that the potential energy curve sometimes is referred to as a potential well. Okay, so the minimum in this particular case for H2 occurs at 74 picometers, 74 times 10 negative 12 picometers. And one thing you'll notice about this potential energy curve, the way it's set up, is that as R approaches infinity, okay, your potential energy, molecular potential approaches zero. That means when this calculation was done, the assumption was when the nuclei are infinitely far apart, we assume the relative energy of the two nuclei is zero. We took that as a zero for the potential energy. Okay, so this difference between that limit, okay, so zero and this minimum, that is your bond dissociation energy. That's the depth of your well. Okay, that's your well depth. It's referred to as bond dissociation energy, and terminal value for that is 436 kilojoules per mole. Now, this green curve that you see here, and this green line down here, okay. Let's see. Okay, can you see better? Okay. That green line is the average kinetic energy of molecules, translational kinetic energy of particles at 298 Kelvin. Okay. Usually, if that level is way below, way considerably less than the dissociation energy, then you're going to find that those two atoms will be bonded under room temperature. Okay. Now, if the well depth is not deep enough, so that, for example, let's say at 300 Kelvin, at room temperature, 298 Kelvin, this is the average kinetic energy of molecules, then you wouldn't expect the atoms to stick together. Okay? And this is a close-up view of that section, this section down here. Oops. Let's take a close-up view of this section down here. Where am I? Right here. In this next slide. Okay? What you'll find is near the minimum of your molecular potential energy, this function looks very familiar, right? That looks like a harmonic oscillator potential, quadratic potential. So your potential energy is some constant K times R minus RE squared. So at very low energies, the movement of the nuclei, you would say, if you were to look at it, think of it in terms of classical mechanics, the movement of the nuclei would resemble that of a harmonic oscillator. So what would, in fact, when we solve for the vibrational energies, you'll find that for low energies, we essentially get the formula for the energies of a harmonic oscillator. So what would be the formula for the energy of a harmonic oscillator? Do you remember? V plus a half times H nu, right? Where V, quantum number V, goes from allowed values of V are 0, 1, 2, 3, and so on and so forth. Right? And what is nu? It's 1 over 2 pi square root of K, force constant K, divided by mu. What is mu? The reduced mass. Mu is mass of nucleus 1, mass of nucleus 2, divided by the sum of the masses of the two nuclei. Okay? Transitions from V equals 0 to V equals 1 will typically, that delta E right there would generally correspond to an infrared photon. Okay, so you probe transitions involving changes in vibrational energy with photons in the infrared. We did that in the lab for a few of the molecules, remember? Okay. Now, if you want to get a better description of a visualization of what the motion of the molecule, the two bonded atoms would be, it's a very nice website to go to. This just do a search for PHET simulations at the University of Colorado. And search for atomic interactions. So search for physics, maybe chemistry, or chemistry simulation. Here's one that's atomic interactions right here. Have I shown you this before? I don't know. Okay. So that's a Java applet. When you download it, you just you'll get a warning. You can just say keep the file, and once it's downloaded, click on it to run it. Where is it? All right, so let's do 2 oxygen atoms. All right. So this is not the actual theoretically calculated potential energy, but this would resemble the potential molecular potential energy for the ground state of O2. And so we imagine we're pinning one atom over here, okay? And then we have the other atom. We're going to move the other atom. Oops, sorry. Right there. And what do you notice? It's just vibrating, okay, from one end to the other, back and forth, back and forth. You have a harmonic oscillator. So this is what we would call a semi-classical view of the motion of the molecule, because you're using theory, using quantum mechanics to solve for the molecular potential energy, but you're describing this motion in terms of what you would expect if it were behaving like a classical particle. But essentially, it's behaving like a harmonic oscillator. Okay? So let's stop that. Let me drag this a little. Can't get my. Can't drag it to the left. I used to be able to easily do this. Let's see. It's locked up on me. Well, anyway, let me see if I can explain that with this diagram right here. The idea is this. If you remember, imagine you have a particle at this distance, let's say 80 picometers. The distance between the two nuclei of hydrogen is 80 picometers. Okay? What this is saying is this. It's as if, okay, there is a force that is pulling that hydrogen, that nucleus of hydrogen towards the other hydrogen nucleus. So as it's being pulled in, what's going to happen? Its potential energy is dropping, so this blue curve is dropping, right? But what's happening as the blue curve is dropping? The difference between the green curve and the blue curve would be your kinetic energy. It will be speeding up, right? So it's just like a harmonic oscillator. It's going to speed up as the potential energy drops, and then it's going to slow down. So once they reach about 74 picometers, they're starting to get too close for comfort there. So they slow down. There's going to be net repulsions between the two, and then eventually they'll stop. So this the closest distance that they'll approach would be about 70 picometers, and then repulsion sets in. Okay. And then so they'll move apart, speed up again, slow down, stop, okay, when they get to this point right here. So what's happening here is your potential energy is going to be dropping, speeding up, potential energy is going to be increasing, slowing down, stop, and then it's just going to keep turning back and forth, back and forth. You have a harmonic oscillator. Okay? Now, if you look at it over a wider energy range, you'll find that in fact you go to higher vibrational energies, it's not a harmonic oscillator. Okay, remember the harmonic oscillator is what? A quadratic potential, right? So if it was a harmonic oscillator, it's the potential, the molecular potential energy is going to look like that. But in fact, your potential energy is going, molecular potential energy is going to approach a fixed value, constant value, as R approaches infinity. So you have what's called anharmonicity, correct anharmonicity. And so the correct energy is not just the harmonic oscillator energy formula. What would we have to do? We have to introduce correction terms. And we did this in the lab. And remember, in the lab, what did we call H nu? Call that omega E. Okay, so you introduce an anharmonicity correction. So you subtract minus omega E x E b plus a half squared plus omega E y sub E b plus a half cubed, and so on and so forth. So you introduce corrections just so you can fit your experimental, your theoretical values to the experimental data. Okay.